Welcome to our lectures on DC microgrid and control system. Today we shall discuss in detail about the modeling of the energy storage, that will be ultra capacitor and the batteries mainly. So, this will be our presentation layout. Today we shall discuss about this ultra capacitor or the super capacitor and its modeling, or thereafter how you will be charging and discharging the ultra capacitor, and thus it will be essentially related to the control charging, that we will talk about the control and modeling part of it. Thereafter we will have a modeling of the secondary battery system and the battery management system or the battery control system, that will be discussed. We try to cover this topic in our course content today. So, what we know, that we have seen that since the eradicate actually uncertain nature of this energy sources in case of the renewable energy, we require to store the energy. So, storing element is essentially one a big part of our microgrid. So, it is well known that energy storage device provide additional advantage to improve stability, power quality and reliability of the power supply sources. And most of the, and in a microgrid also there might be a peak demand, and also there might be a some time where you are generating the source at its peak output. So, there is a mismatch between these two peaks, but it may cater the average power throughout the day, but there will be a instantaneous mismatch between the peak demand as demanded by the consumer and the supply generated by the renewable energy sources. And for this reason, it necessitates to introduce this storage element. The major type of storage devices being considered today include batteries. With the advent of the lithium ion batteries, thereafter other batteries, we will see that there is a lot of advantage to it. Thereafter supercapacitor and the flywheel energy system. And you know, actually this the storage element will have its requirement depending on the time. Battery can supply power in hours, ultra capacitor will last for the generally in minutes, and flywheel also almost same thing depending on the size of the flywheel, because you know its energy storage capability is actually is a rotational mass, its inertia constant and all those things matters. And so, you will have you will require different kind of utility for support, different kind of, if it is a voltage fluctuation kind of application, generally ultra capacitor or the or actually voltage fluctuation kind of application, you got a huge voltage sacks sometimes, and this is the issues related to the power quality. Then we will go for the ultra capacitor and the flywheel systems. And if you wish to shift or manage your peak power demand because of mismatch between your peak demand and the peak generation, battery generally preferred nowadays. Of course, you know technology is emerging and many are working on it. So, of course, what we are making a statement in 2019, it can change within 5 years. The performance of the batteries, superconductor and flywheel have over the years been predicted through many different mathematical models. So, we shall come into its mathematical model, we shall take few simple mathematical model to analyze the storage element, and ultimately overall control system will understand the mathematical model only. So, we require to develop the mathematical model of this storage element. Some of the important factors that need to be considered while modeling various energy storage device include its storage capacity, mostly it is the energy. So, battery will have a stored charge in form of the chemical energy. Ultra capacitor or super capacitor will store the energy of half C V square. Here it will be storing the energy of half m r square into omega. And also the rate of, that is also the power part of it. Rate of charge or discharge, this is basically if you differentiate energy you get power. So, and which rate it can deliver power into the system. And the temperature sensitivity, because battery has a huge temperature sensitivity, we require to consider it, and its whole life, how many years it will last, that also required to be considered while choosing a storage device. Let us take the ultra capacitor or the super capacitor first. Super capacitor can be modeled by the equivalent electrical circuit, because you know that is a capacitor only. So, it has to be a capacitor, ideal capacitor, followed by series and the parallel resistances. The super capacitor is characterized by the capacitance C and two resistances. Series resistances R s, commonly called the equivalent series resistance or ESR, and ESR should be very small, which is the main contributor of the power losses in the charging and discharging process, and the dielectric leakage, then that will be modeled as a resistance RL. The voltage at the supercapacitor terminal can be deduced from the equivalent circuit of this figure. So, you can have the what is the voltage available to you, you can calculate. So, while charging, the terminal voltage can be derived that ut equal to uc, that is the capacitor voltage, plus the drop across the ESR, and in turn the voltage uc can be actually derived from this uc by dt equal to I1 minus I1 by C. Most of the cases, you know, actually this resistance is quite high and this resistance value can be neglected also, where the current through the load I is a leakage current, which can be expressed as I1 equal to UC by RL. Generally this current is very small, and thus therefore we can also substitute that this I here, and ultimately you get UC by dt equal to I minus UC by R by C. So, this will be the actually the dVdt across the capacitor, essentially this will be the current which will sink through while charging. So, let us take a buck converter which will be actually storing the ultra capacitor in charging and will be discharging by the bidirectional DC to DC converter in a boost mode. So, in this configuration the voltage DC link Ui, that is this one, is considered to be constant, and as shown in the figure 2, it has two states, one referring to the voltage UC, other referring to the voltage to the other, actually this will be the current through the inductor. There are two states always, this is a voltage across the capacitor and current through the inductor. So, we can rewrite that equation 4 determine the dynamic voltage of the capacitor. The dynamics of the inductor current can be expressed as L di dt plus ut equal to duty cycle when it is on, or d is the duty cycle of it, into Ui, where Ui is the input to the buck converter, where dt is applied to the time dependency of the converter. So, thus what happened, the duty cycle varies between 0 to 1 and it relates the input and the output voltage of the DC to DC converter. So, U equal to Ui into D. The duty cycle D serves as an input to the switching schemes for the power switches of the converter. Ideally the converter could provide any magnitude between the boundaries of ut. However, due to the practical limitations and performance of the controller, it is preferable to constrain operation to the continuous conduction operation region, because control is always better in a continuous conduction mode. Then actually this equation will hold, otherwise it does not hold, and the equation 4 and 5 can be used to build the dynamic average model. Please refer to the advanced power electronics NPTEL courses in DC to DC converter. I have discussed in detail about the average modeling of the DC to DC converter, a model of the coupling of the DC to DC converter for the supercapacitor. Now, this is a scheme of charging ultracapacitor. You got ut, that is the reference ut, the control cascade control of the storage side of the super ultracapacitor, and you will decide the mode from here, and you have got the ut reference, that is basically the desired voltage is the ut of the ultracapacitor, and essentially you have a PI controller, and PI controller will have also a feedback mechanism, that a limiter, and ultimately that gives you effectively the value of the R. So, this reference will be actually compared with the average current controller. You can have a peak current controller also, but it is better to use the average current controller, and ultimately that will decide the duty cycle of the buck converter in this case. So, this is the explanation of this figure. The dynamics of the capacitor voltage is shown, is given equation 4 are much slower than the dynamics of the inductor current given in the equation 5. So, for this reason you have a first controlling current loop, that is this one, and thereafter you have a slow controlling voltage loop. This suggests that a cascade controller should be designed in which the inductor current is controlled by an inner first current loop, which receives the current set point from the output of an outer slow control loop for the capacitor voltage. Figure 3 depicts the proposed topology for the control system. This is the figure 3, and let us split it into the and we shall here discuss about the inner current loop or the inductor current loop. The design of the control for the inductor current is based on the equation 5. Please refer to the equation 5. It is the inductor current. So, this is the equation 5. In Laplace domain, one can derive the transfer function, that is GIS, for the DC to DC converter. Essentially it is a discontinuity for switching on and switching off. So, for this we will have a average model, and this transfer function provides the inductor current Is as a function of the duty cycle ds, and the voltage between the ultracapacitor terminal voltage UTS. The voltage of the DC link Uy is considered to be constant. The addition of the controller CIS of the current Is results in closed control scheme as depicted in figure 4. So, this one is basically the CIS, is additional controller, that is basically compare this current loop that will fit to this a gain element to match this dimensions as well as its magnitude, that will control with the battery this ultracapacitor output voltage, and then you got a 1 by Ls, that is inductor, and ultimately this current is the current through the inductor. This is the inner current control scheme. And now let us come to the voltage control loop. The design of the capacitor voltage control loop, the equivalent circuit of the capacitor in the figure 2 can be simplified by neglecting the ESR and RS and the leakage current RL. So, we just neglect the ESR and the RL and just you write C dV dt equal to I. This is because the voltage dynamics will be mainly generated by the capacitance C and only it will add up this value of the voltage. So, rate of change of voltage if you differentiate it has a no sensitivity on the resistance. So, for this reason it is eliminated. If you have UT plus some I into RL, so actually if this part is constant, so it does not make any sense. So, by doing this following relation can be established. While in a Laplace domain we can formulate the transfer function that is G u c and which provides the supercapacitor voltage ut. So, that can be written as ut by I s, essentially it will be it is 1 by C s. So, according to this u c, the supercapacitor or the plant can be considered as pure inductor linear system, and it is proposed that this should be controlled by a PI controller structures with the transfer function of CV. So, this is the by this analysis we now understood what kind of controller is required here. This is CI and we require another controller. So, that we have to go back to this slide. So, for this is basically the voltage controller and this is essentially what you can see that it is a PI controller. So, this controller will provide the reference current for the inner current control loop as a function between the error between the UT and the actual capacitor voltage. So, accordingly we will charge that, and this is the analysis of this ultra capacitor and it is used for stabilization of the loop as well as it is used for stabilization of the transient disturbance for the load change or the drooping and other phenomena also. And in a DC microgrid, ultra capacitor nowadays is an integral part of as a storage device. Now, let us come into the modeling of the second storage element, that is battery. Battery essentially is a slow element, it takes lot of time to charge as well as discharge. So, its phenomena will be in hours, but essentially your energy conservation and all those things will be balanced by these batteries only. So, there are several approaches for modeling the batteries and some of them are electrochemical. So, we cannot dig into that because of our limited knowledge in the electrochemical processes, but we shall do the analytical study, stochastic study and its electrical circuit models. So, each type represents to a greater or lesser extent specific phenomena in the battery cells. For example, state of charge and the capacity variation, the temperature difference, aging effect and so on. So, life of the battery also depends how much cycles you have charging and moreover how much you are discharging in each cycle. So, this model should accurately represent this. For example, if you go for the 50% depth of discharge and you may able to actually you can refer to the data sheet of any battery companies, you can have a charging cycle of 5000. If you go to depth of discharge, mind it 80%, you will find that you may limited to go to the level of 2500. More the depth of discharge and less will be the number of cycles you can use. So, your model should validate those all phenomena, chemical phenomena mathematically. But there is a great challenge in it. However, none of this approach is currently accurate enough to represent all of the factors affecting the battery performance of its own. Thus, modeling should be adopted for the specific requirement or specific needs. And for example, if you keep in the battery into the sensitive temperature control environment, you will find that it will last long. If you put that batteries in non-AC environment, you will find that they are going to decay faster. Electrochemical models are based on the complex nonlinear differential equations, and that allow us to produce the electrochemical process within the battery cells, but that is totally the domain of the chemical engineers. These models are most detailed ones among those considered, but also hardly implementable in the dynamic simulation environments. Of course, it is a perspective of an electrical engineering. So, maybe actually a person with the we have definitely a limited knowledge with the chemical processes, chemical thermodynamics, and for this reason we are making this statement. But problem lies, they do not understand electrical engineering, we do not understand a good amount of the chemical engineering. So, for this reason the solution we wanted to see here is a stochastics aim to reproduce cells capacity nonlinearities from probabilistic method based on the physical characteristics of the battery cells. So, there are people still working on it, but we try to have a simplify our problem and try to address it. And look, it would have been a great, actually now what happened in your battery mobile, it gives the state of charge. How it estimates? It generally actually estimates by the output voltage, but it is silent about that how many years left it will has to be replaced. So, how many charging and discharging cycle you have followed. So, battery management system is a huge process, and warning system should trigger that I require to replace this battery within this period of time, something like that. Like your oil gives an indicator that I have to fill oil once actually the level of this oil goes low, but battery when it will be replaced, it is difficult to give a warning. And anyway, we adopt some probabilistic method to forecast on it. These are also hardly implementable in dynamic simulation environment as for the case of the electrochemical models. These models rely on Markov chains. So, this is altogether a chemical process, and for this is an analytical model aims to reproduce the cell's capacity nonlinearity such as the capacity of the rate of dependency and the capacity recovered phenomena using fewer equation and with the lower order than those formulated in a electrochemical models. And thereafter it allows successfully to include this model in dynamic simulation environment in order to predict the SOC. SOC generally if you wish to predict rightly, we require to calculate the specific gravity. Specific gravity generally changes of the battery due to the chemical reaction. However, they cannot be used to represent the IV characteristics for the batteries or their dynamic behavior. For example, analytical model of Picou's law of the diffusion model and the kinetic battery model can be used here. The electrical model is based on the electrical circuits which allows to produce IV characteristics that we require to know, for the batteries and also their dynamic responses. To do so, these models are based on controllable charge and current sources in combination with usually variable resistance and capacitor. Let us see. So, this is Cepheid models and the Picard's law. Because of their simplicity and maturity of one of the most utilized alternative to build up an average dynamic model is the Cepheid model. The battery cell or the module adopted this model resembles a voltage source connected in series. The magnitude of this voltage source is variable depend on the SOC and other nonlinearities. So, terminal voltage of the battery while discharging is computed by the following equation. So, this is the terminal voltage US, K we shall explain it, Q by QIT into I minus RI into A e to the power B I T Q. So, it is a complex relation, it is called this law, Picard's law. And in charging process, just see that what is the difference between charging and the discharging process. So, it is almost same, just it will change little bit, and you will have UT US minus K Q by IT into R RI e to the power this. So, let us introduce those nomenclature here one by one, where UT is the terminal voltage in volt, I is the electric current in amperes, and Q is the maximum amount of charge in the battery, that will be actually your ampere hour capacity of the battery. Generally, it is been denoted by the manufacturer, and it is the actual battery charge in AH, and US, K, R, A, B are the Cepheid parameters. These Cepheid parameters are defined as US as a constant voltage in volts, K is the slope of polarization curve or the polarization resistance, and R is the internal resistance of the cell, which you talk about many time from class 2 level of the cells measured in the charge state. A and B are the empirical parameters. The Cepheid model of the electrical potential drops in the battery cell during the discharging process is divided into the 3 parts, each of which depends on one term of the equation 9 that we have seen there. The term 3 depicts the nonlinear voltage drop at the beginning. So, this is the case, beginning of the discharging process starting from the full charging state, this is the process. The term 2 and 3, just go back please. So, this is the term 1, this is term 2 and this is the term 3. Nonlinear voltage drop at the beginning of the discharge process starting from the full charge, and so experimentally you can find it out A and B. So, terms 2 and 3 determines the potential drop due to the internal resistance, and you can see the figure B, that is the nominal zone, and this is the for the term 2 and term 3. And finally, the end of the discharge. So, it will be very fast and you require to operate in this region only, this is called your safe zone of operation. And you see that actually you may see that when you got a 40% battery charge, it goes to the 30% battery charge in that kind of time, and the battery charges it goes to 10% to 0% almost in a no time. So, this defines this characteristics, and finally, the first part of the equation determines the exponential potential drop while exhausting the cell's charge S, and it appears to approximate the value of the Q. So, based on this model we require to first design the battery charging process. In case of the ultra capacitor, a cascade control system based on the PI controller can be proposed for the batteries. So, same model can be used. In such a structure, the linear control loop should be in charge controlling current exchange by the batteries. The control loop topology and the turning are identical to those of the ultra capacitor. Please refer to the ultra capacitors. Since they solely depend on the inductor, include the DC to DC converter and the voltage at the DC link that couples the storage side of the converter to the DC bus. However, the outer control loop in charge of providing the inner one with a reference profile of the current. The reference current is limited by the battery management system for the protection purpose, and generally if it is a lead acid battery, so your maximum charging current cannot cross 10% of your AH value. So, that kind of limitation will be put by the battery management system. And the reference profile of the current and the design of the control for controller greatly depend on the final application of the battery. You can see that there are different kind of charging, that is called CC or CV charging. The current profile are further differentiated by charging and discharging process. Battery data sheet usually include voltage and the current profile to be applied at the battery terminal for carrying out so called constant voltage or the constant current charging. So, this is the capacity in AH, and this is the constant voltage charging. Thereafter, you can see that this is basically what after that this is called constant power charging essentially, because voltage into current is constant. So, there are different kind of charging methodologies. So, the constant current charging mode, if you provide a constant current is applied at the battery terminal and it is ensured by the current control loop of the DC to DC converter which the battery is attached. The battery cell should be properly monitored so that it avoid overcharging and over discharging, that is we require to ensure that, otherwise there will be a first fall or first rise in voltage. Once the cell voltage reaches the peak charge, the controller switch to the constant voltage mode. The constant voltage control mode, the control aims to prevent the cell's voltage from dropping from the level it is maintained. While in this control mode, the battery cells becomes completely charged and thus current entering into the cells drops progressively and lowers down the maximum value. Then there will be a charge cutoff occurs as soon as the predetermined minimum current is reached, indicating that the full charge is battery is fully charged. So, this is the way your battery management system will work. The charging and discharging of the battery cell can be governed by the cascade control system of the PI controller, and the voltage cells the voltage at the cell terminals is affected by the several nonlinearities within the cells, such as the dependence of the capacity and at which the rate is charging and discharging, temperature, other capacity recovery, parameter variations, SOC and so on. So, all cannot be fed into the modeling. For this reason this formula is empirical one. So, but while following that we can successfully implement the battery management system. Thank you for your attention. We shall continue to our next discussion on the storage element.